This is Charles Thacker's Tiny 3 computer, which was an idea of Alan Kay's. Alan Kay said, "I'd like to show JHS and HS, junior high school and high school kids, the simplest non-tricky architecture in which simple gates and flip-flops manifest a programmable computer." Sorry about the reflections. What happened to his silk screens? Too expensive. Alan posed. Chuck Thacker worked at Xerox on the Alto, one of those early mouse computers. Why can't I get rid of this stupid... Alan posed a couple of other desiderata. Primarily, the computer needs to demonstrate fundamental principles, but should be capable of running real programs produced by a compiler. This introduces some tension into the design, since simplicity and performance sometimes are in conflict. This sounded like an interesting challenge, and I have a proposed design. It's a Harvard architecture. This separation of program and program data and instruction memory is not what I ever understood differentiated von Neumann from non-von Neumann. I thought von Neumann meant you have a kind of central processing unit. Maybe it's because of modeling and people trying to, I don't know, because self-modifying code gets too complicated when you have caches and things like this. Or is it just because the kind of model checking approach to verification just completely fails when the machine state can fold back on the semantics? I don't know. But I don't really see the difference of what if you connect two of these Harvard machines together and have them programming each other? Don't you just get the same problem? But I'm not particularly interested in finding bugs in CPUs. I'm interested in being able to use all the junk that's out there. I mean, how many computers and smartphones have been manufactured? It executes each instruction in two phases, corresponding to instruction access and register access and ALU transit. Yeah, 2 or 3. There's some parentheses in there which she hasn't put in. Registers are written at the end of the instruction. Figure 1 is a block diagram of the machine. It has in data ALU, some sort of bus coming from here. A block of memory, a high-speed memory that so you get register addresses and write addresses. Wow. The program counter. Some external memory. Ben Eater's videos. What is Ben Eater's machine design missing from this? He's got 2-phase execution. Although it is impractical today to build a working computer with a handful of gates and flip-flops. No, that's not true. It seemed reasonable to implement it with an FPGA. Yes. Current FPGAs, I mean, not when he wrote this, but you can implement 128 6502s on one of the, last time I checked, one of the higher end Xilinx gates. Xilinx sells evaluation boards for $150 that includes, oh dear, an FPGA and some auxiliary components for connecting the chip to real-world devices and a PC that runs the design tools, which are free to experimenters. He wrote this while he worked at Microsoft Research in September 2007. He died 10 years later of complications from esophageal cancer. Anyway, Simon Moore sets this as an exercise for Cambridge undergraduates, so Anthony Fox et al. Gives an L3 specification of the semantics of the whole thing. Apparently, it seems very, very, very small. So maybe that's an exercise. I'm thinking about all this model checking and blah blah. The page I accidentally clicked on my phone was Scott's trick. This was probably, I always read something like that, I imagine Thomas Forster wrote it or edited it, or his students or something. And in it, there's an article on the axiom of regularity, a reference to the article on the axiom of regularity, the cumulative hierarchy and types. It's von Neumann again. Enderton wrote that the idea of rank is a descendant of Russell's concept of type. Comparing ZF with type theory, Alasdair Urquhart wrote that Zermelo's system has the notational advantage of not containing any explicitly typed variables, though in fact it can be seen as having an implicit type structure built into it, at least if the axiom of regularity is included. Scott, 1974, went further and claimed that the truth is that there is only one satisfactory way of avoiding the paradoxes, namely the use of some form of the theory of types. That was the basis of both Russell's and Zermelo's intuitions. Indeed, the best way to regard Zermelo's theory is as a simplification and extension of Russell's. We mean Russell's simple theory of types, of course. The simplification was to make the types cumulative. Thus, mixing of types is easier and annoying repetitions are avoided. Once the later types are allowed to accumulate the earlier ones, we can then easily imagine extending the types into the transfinite. Just how far we want to go must necessarily be left open. Now Russell made his types explicit in his notation, and Zermelo left them implicit. Square brackets, emphasis in original. And the emphasis is on explicit and implicit, and extending and cumulative and simple. It's interesting. The axiom of regularity, together with the axiom of pairing, implies that no set is an element of itself, and that there is no infinite sequence AN such that AI plus 1 is an element of AI for all I. With the axiom of dependent choice, this result can be reversed. If there are no such infinite sequences, then the axiom of regularity is true. Hence, in this context, the axiom of regularity is equivalent to the sentence that there are no downward infinite membership chains. The axiom is the contribution of von Neumann, 1925. It was adopted in a formulation close to the one found in contemporary textbooks by Zermelo, 1930. Virtually all results in the branches of mathematics based on set theory hold even in the absence of regularity. However, regularity makes some properties of ordinals easier to prove. and it only allows induction to be done on well-ordered sets. And it not only allows induction to be done on well-ordered sets, but also on proper classes that are well-founded relational structures, such as the lexicographic ordering on pairs n alpha, where n is an element of the least upper bound of omega, and alpha is an ordinal. Given other axioms of ZF set theory, the axiom of regularity is equivalent to the axiom of induction. The axiom of induction tends to be used in place of the axiom of regularity in intuitionistic theories, ones that do not accept the law of the excluded middle, where the two axioms are not equivalent. No infinite descending chains. What do you, when you verify these things, what are you really trying to get at the bottom? That there are no errors, that there are no things, such things as cosmic rays that come in and change the state of your CPU? Is that what you're trying to, you're not trying to prove that. We've got thousands of these fucking computers all over the place. All we want is to put them together in something that actually serves us. And not just keep having to throw them in the fucking landfill. So that we can make more money selling new ones. That's all I'm trying to do. Just make a computer system that works and that people can communicate. So that when you have situations like a government that's bombing the shit out of a refugee camp and saying that people should leave the north and go to the south, and they bomb the road, and so that we can find out whether the road is actually open or not, and how to get people through and stuff like that. That's an extreme example, because none of that shit should be going on anyway, but it is. But when you have a climate catastrophes and things like that, you also get situations where you really need to know what the hell is going on. And you don't want to find that your 4 gigabyte memory computer isn't good enough to enable you to connect to the fucking internet. We don't need to know that every single device works and works correctly. We don't even need to know whether they're secure. You just want to know that the system bottoms out at some point. I think you need to know where that point is, or the decide anything about it.